Welcome back again. What I wanted to do today is to give you a first introduction to the Project 2 variant, where we are going to study the same problem which we had in Project 1, but now using neural networks and so-called Boltzmann machines. So I'm going to start with Boltzmann machines. And then after the break, we will have one or two sessions where we're going to discuss the implementation of neural networks in order to solve Schrödinger's equation in the same way as we did in Project 1. That means we recast Schrödinger's equation, a coupled ordinary differential equations or partial differential equations if you're dealing with time, where we recast them as a stochastic integral and where we use the variational Monte Carlo in order to obtain the energies. So to remind you a little bit of what we discussed last time. So we have essentially now two project groups. One group who has expressed a clear interest in working with Boltzmann machines and neural networks. So what I wanted to give you now today is, for those of you who have worked with the neural network, this is going to be a repeat. And for those of you who are not too familiar, I wanted to give you some of the basics there, but I wanted to point to how you can use these Boltzmann machines, which is a kind of direct implementation of neural networks, a specific neural network method applied to the system which we started in Project 1, where we now are going to essentially replace the trial wave function with a neural network, which is now given by what's called a Boltzmann machine. So I also want to give you the links to the material, which I'm going to use. Then after the break, we are going to look at how we can replace the wave function, and in particular the correlated part of the wave function, using a neural network. So this is going to be a kind of two-step process. The easiest way to implement these things is to use a Boltzmann machine. A Boltzmann machine is essentially a Boltzmann distribution with parameters which are being trained by a neural network. It's a little bit easier to set up than a standard neural network, and that's why I wanted to start with a discussion of Boltzmann machines instead of jumping straight into neural networks. The reason for that is that implementing a Boltzmann machine is something which, one, can easily define Project 2, so we can actually stop there. Alternatively, we can move beyond the Boltzmann machine and also implement a neural network. So these are things which I want to discuss with you in the special sessions which we have now. Then we have another group which has expressed an interest to work on path integral Monte Carlo methods. We will not have dedicated group sessions, so that means that those of you who are interested in that topic, you will have more to deal with this as a kind of special study, and then we will meet at the lab and discuss complications or problems which you may have. So the basic idea now, from now until the end of the semester, which is May 12th, is to discuss the implementation of Boltzmann machines and neural networks. So if you now, just to quickly remind you of the alternatives, so basically what is the main alternative which people have opted for is a continuation of Project 1, where we discuss Boltzmann machines. Now, any questions from you guys? I mean, about the practicalities for the rest of the semester, things which are unclear or things you would like to bring up before I now move into the material which is of interest for us. Any questions? Feel free to unmute yourself if you have questions, or just use the chat functionality. Okay, so there doesn't seem to be any questions. So I wanted to give you the link to the material which I will be covering now. So the first step, if you now click on the Jupyter book here, and if you scroll down, you will find the material on deep learning. And for those of you who have taken the course Physics SDK 4155 or 3155, you've already been exposed to neural networks and you will recognize the material here on neural networks. So what I wanted, on the other hand, is to jump into the topic of Boltzmann machines, which is something which allows us to make a, how to say, an easier transition to the topic of deep learning, where we can almost immediately go from project number one and simply replace the trial wave function with another trial wave function. So let me try to explain to you on the whiteboard the kind of overarching philosophy which we are going to deal with. So I'm going to switch to the whiteboard, and let me try to bring up the basic philosophy which we are going to cover now. So the project 2 variant with Boltzmann machines and neural networks. So I've split this in two here. And I want to roughly explain to you what we actually are going to do. And then there is the topic of neural networks. So if we look back to project number one, which we dealt with, we had in project one, we had a trial wave function, psi of t, t for trial again, which contained a collective variable which expressed all the coordinates of the different particles. And then we had a set of variational parameters. And the way we wrote the wave function, we had one part, which was a product of single particle wave functions. That was the harmonic oscillator part. So we wrote this as a product of I equal 1 up to the number of particles. And then we had the single particle wave functions, which were the harmonic oscillator wave functions, R of I. And these functions could depend on variational parameters. Some of them, a subset of the variational parameters, or all of them. In our case, the basic variational parameter was the harmonic oscillator parameter, which we used in the trial wave function. So these functions were, in our case, in project number one, they were just given by a Gaussian multiplied with some coefficients. And essentially, that's the leading part of the harmonic oscillator. And for the harmonic oscillator, with particles being placed in the lowest single particle state, this is essentially an exponential with the argument squared times a constant, which in our case was the variational parameter. But then what we had next is the part which is difficult and which normally cannot be compared with an analytical solution. And that's the part which comes from the interaction. So that means that what we had then was something which we call the Jastro factor, or the correlated part. So we put a C on it. And this could also be a function of all these variables, and also the variational parameters. So I'm just putting in the dependence on the variational parameters as a kind of collective variable. So this was what we normally call the one body part, because we had a well-defined single particle basis. And you saw also in project number one that most of the energy came actually from the harmonic oscillator part. So when you calculated the non-interacting case and you compare that with the interacting case, the energy difference wasn't that large. This is the system which we were looking at in project one is an example of what we normally call a weakly interacting system. It means essentially that the expectation value of the potential energy, the two-particle potential energy, is much smaller than the expectation value which comes from the one-body part of the Hamiltonian. In our case, the one-body part of the Hamiltonian was given by the harmonic oscillator potential, plus the kinetic energy. And this part is the largest part, or gives the largest contribution to the ground state energy. So this piece which you see here, which we are highlighting here, this is actually the difficult part normally. So what we are going to do now is to replace that one. Instead of using a fixed function, which we had in project number one, we are going to replace this one either with a Boltzmann machine. This is actually a Boltzmann probability, but we are going to label it Boltzmann machines to stay in tune and sync with the kind of deep learning language, or we can replace this one with a neural network. So I'm going to use an acronym NN for neural networks. So this is a neural network. And we are going to discuss how to do that after the break. Now, alternatively, what you can do is now to take, so this is an alternative 1, an alternative 2 here, and which we are going to explore as well. So this is what we might call this alternative 1. So in project 1, we did that. So what we are going to do now is to set this up as an alternative 1. And this alternative 1 means that we are going to replace the correlated part of the wave function with a neural network. An alternative 2, on the other hand, is actually to let the trial wave function, which we have, psi of t of r, and a function of the parameters alpha. Now, the parameters alpha now are not going to be the parameters of I would say the variational parameter, but they are going to be expressed by the parameters of the network. So our network is going to be given by weights and biases when we are setting up a neural network or a Boltzmann machine. And that means that what we will end up with is an optimization problem, which is similar to the one we had before. So essentially all the machinery which we have dealt with in project number 1 is something which we are going to reutilize in project number 2. So the alternative 2 is something which normally gives a worse result because it's less guided, and there's also a problem with a neural network in obtaining the right symmetry. So we're also going to use for the Boltzmann machines, I'm just going to use a BM or a BM. So it's interesting to compare these two alternatives. This is like you making a fit to a function using a neural network, and you try to guide the neural network in some way based on your insights. And then the remaining part is something which you let the network find in an optimization process. So the two alternatives which we're going to explore is one, where we try to guide the trial wave function with some minimal physics input. And in our case, this can be the harmonic oscillator part, or the product of single particle wave functions, which we had from project 1. So in project 1, what you found then was an optimal set of parameters, alpha, for the harmonic oscillator part. So what one can do then is to take the optimal single particle piece, which you got from project number 1, and then in this alternative 1, let the neural network obtain or find the best correlated wave function. Then in alternative 2, you can just let the neural network find out what is the best representation of our wave function. So any questions so far? So this is a basic overarching philosophy of what we are going to do in project number 2 here. And the first step we are going to look at is the implementation of a Boltzmann machine, which is a little bit easier than implementing a so-called standard neural network. Any questions with this kind of overarching philosophy? So just keep in mind that when we are doing a Monte Carlo calculation, so we are going to do a standard Monte Carlo calculation, but the trial wave function is now given by a so-called Boltzmann machine. So one thing I need to give you a kind of overview about before we move on is some of the basics of a neural network. Now, the thing which I wanted to say something about is the setup of a Boltzmann machine. So let's now dive into Boltzmann machines, and gradually when we deal with this, we are now going to discuss the basics also of a neural network. So let me just start discussing the Boltzmann machines. And at the end of my notes on Boltzmann machines, you will also find an example code which solves this problem which you see here for a harmonic oscillator basis. And we're going to come back to that code after the break. So if we look at Boltzmann machines, what we essentially are going to do now, if we look at the trial wave function, so the simplest thing, if you think of this alternative 2 here, what we are going to use now is that the wave function is being replaced by a Boltzmann distribution. So in essence, what if we look at a neural network, what we would have, if we now look at the basics of a neural network, and a Boltzmann machine is a neural network, except that it's a neural network where we keep generating new input variables. In general, a neural network has a fixed input. So if you now think of the basics of a neural network, what we would have is an input layer. And in our case, the input layer would be the coordinates of the trial wave function which we have. So if you look at the quantities which we have here, these RIs, they would now define the type of input to the neural network. So the input now, if you now think of your vector R, so the input layer contains now the vector R. So the different input nodes, if we write them down like this, they could now contain the positions of the different particles. And if we are dealing with a one-dimensional problem, just to make life a little bit simpler in this kind of overarching picture, so you could now have particle 1, so I'm not putting vectors here, so R2, R3, and then you go down all the way to particle N. And since we're just dealing with one dimension, we could just call this X1, X2, and so on. So this is normally called the input layer. And we're going to box it in like this. So a standard neural network has now a given input layer. And then this input layer feeds into a set of hidden layers. So let's just write it. So we're now just setting up one hidden layer. So we have a hidden layer here. Now, these hidden layers, they contain a given set of units or nodes or neurons, as they are being called. And we are going to label this with H's. So there's going to be a node H1, H2, and this does not need to match the number of input nodes. So that's why I'm going to write this as an H of M here. So M may be equal to uppercase M, or it may be different. So these are parameters of your theory. Now, in the theory of neural networks, there is a theorem which is called the universal approximation theorem. And that says that a neural network can approximate a given continuous function to a certain error with at least one hidden layer. So this is an extremely powerful statement, which simply states that we have an approximation to an unknown continuous function, which can also be complex, which we can fit to a given precision by using at least one hidden layer. Normally, neural networks fall into the category of what we normally call deep learning. So we can make actually these networks deeper and deeper, so we can have more hidden layers. That means that we will have more parameters. So ideally, such a neural network, when we are now setting it up, is something now which, so we just mark this with another color. So these are linked now with the input nodes. So we would typically have an input to the first hidden node from the first input variable. This can also feed into the next one, to the next one, And then this goes all the way down to the final one. And we would have the same for the next nodes which we have here. So we would now have an R2, which feeds into H1, H2, H3, and then I just put dots here and all the way down here. And then I'm just going to put a kind of generic label for all the other ones. So that means that we are going to have just some generic dots here and arrows like that. So this is a network which is fully connected. What it means then is that there is a parameter which links R1 with H1, and that would be called a W11. That's called a weight. This is an unknown parameter. And these parameters play the same role now as the variational parameters in a standard variational Monte Carlo calculation. So we would have a W12 here, and et cetera, and then we would have the final one, W1M here, which connects the first input node to the first hidden node. Now, this universal approximation theorem, that doesn't say anything about the number of nodes and the number of hidden layers which you need in order to reach a specific precision. Now, the hidden layer, so now we are making a neural network with just one hidden layer. Now, these different nodes, they can now produce one output. So in our case, one output could be the value of the wave function. So this could be psi of t of these r's. And now we're going to write a new parameter, which I'm going to call theta, with a vector sign on top of it. So theta is now going to be a collective variable for the weights, which I write like a matrix W. And then there is a set of so-called parameters which are called biases. So to every such hidden layer, there will also be a bias parameter. So there will be a parameter B of M, B of 1, B of 2. So these are new parameters which are often used to initialize the nodes in case there is a zero input to a given specific node. This is simply to hinder that the learning of the network does not stop. So if there is no input to a given hidden node, then that hidden node will produce a zero output. So in the training, this is a situation you want to avoid, because then the training would stop. Now, what happens now is that all these hidden nodes, they would then conspire to give an output. And this output is now something which feeds into the final output layer. So this is normally called the output layer. Now, this output layer, in our particular case, is something which we cannot compare to an exact wave function because we don't have the exact wave function. So in a standard neural network, the output which you obtain will be compared to some data which you have labeled and which you want to reproduce. This is a standard setting in a neural network. Now, in our case, when we are going to look at a so-called Boltzmann machine, we are not going to have an output layer. We are just going to have an input layer and a hidden layer. And we are going to keep changing the input variables till the energy function, or the Hamiltonian which we have, is going to reach an optimal value. So we are going to minimize the Hamiltonian so that at the end reaches its optimal minimum by simply iterating back and forth between a hidden layer and an input layer. But now the input is going to be changed. So the difference between a Boltzmann machine and a standard neural network is that the input layer keeps generating the input again and again. So at the end, what you're doing is to optimize the energy so that you reach your desired energy minimum. A standard neural network, on the other hand, when we are now dealing with the, if we are running this as a neural network problem, is that we are going to have the input fixed, and then we are going to optimize these wave functions so that the energy reaches a minimum at the end. So this means that we have to, the consequence for this is that we are going to reuse the derivative of the energy as we did in project number 1. So we will need the gradients in the training here. Everything which we developed in project 1 is something which we can reutilize in the discussion of either Boltzmann machines or standard neural network applications to the problem. So what you see here is the basic of a neural network. And what you will be doing when you implement this, when you have an output here, is that then you will calculate the energy. Then you're going to use something which is called the backpropagation algorithm, which we will discuss a little bit more in detail after the break. And this backpropagation algorithm is the one which is going to optimize the energy so that we can reach the proper minimum. Now, if we now look at the Boltzmann machine, this is something which is slightly different from a standard neural network. So let's look at the Boltzmann machines. They are normally called generative models because we keep generating a new input. So the way they are set up is that we have an input layer. And then there's going to be a hidden layer. You can stack these Boltzmann machines with more hidden layers. Now, the problem with many of these Boltzmann machines has been that they are difficult to train if you add more hidden layers. So what you would have now is the same type of input as you had before. So I'm just going to write them like this for the one-dimensional case. So I would have an R1, an R2. So these are the positions of the particles. And then we're going to have a set of hidden nodes. And these are going to be labeled H1, H2. And in most cases, you end up with the same number of hidden nodes as you have input nodes. But let's keep this different in the beginning. And then when we're going to set up the code, we are going to, in most cases, we're going to have the same number of hidden nodes as we have input nodes. Now, these nodes are obviously connected. There is no connection between the nodes in a given layer. So it means that what we are going to have now is a connection between this node and that node. So this gives us parameters, and we will have weights here. There will be a weight W11, which we need to optimize in the optimization process. There's going to be a weight 12. There's going to be a 13 here, and this goes all the way down to the final one. In addition, we are going to have biases. So there will be a bias BM. There's going to be a bias into this one, a B1. There will be a similar one here to B2, a B3, etc., all down the line. And similarly, we are going to have connections between Rn and Hm. So this is going to give us a weight N of M, etc., etc. So it means that we are going to have a matrix of unknown parameters, which are now given by the dimensionalities of the number of nodes in the input layer times the number of nodes in the hidden layer. So the unknown parameters are given by a matrix W, which is going to have a dimensionality of N times M. And this matrix now is going to be given by the weights of which connect the hidden nodes with the input layer. So we're going to have W12 and all the way up to W1 of N. And this goes down all the way down to Wn1 and up to Wn times M. So that's the matrix which contains the unknown parameters. And then we're going to have a vector here, B, which is now simply going to be given by the number of biases which we have. And this is actually to be able to start the network in case the weights happen to be 0 by accident. And this goes down to B of M here. So these are going now to be the parameters of the theory. Now, what we are going to use, as if we are thinking back to this alternative 2 here, is to set up a trial wave function, psi of t, of r. And now we are using this new collective parameter, theta. And theta is a collective parameter for the unknown. Let me not put a hat on top of it. Theta is going to be a parameter now which contains a collective container for all the unknown parameters, the weights and the biases. So sometimes I'm going to be a little bit sloppy with vector signs, and hope you can forgive me for that. Now we are going to replace the wave function with a Boltzmann probability distribution. This is the simplest approach we can make. So what happens now is that this is going to be given by a distribution where we will have a function which depends on r and these parameters theta. And if you now think of the Boltzmann distribution, this is given by, and this is why these are called Boltzmann machines, there's going to be a partition function, which is now a normalization factor. You would have an exponential of 1 minus some parameter t. This could play the role of temperature, but we are going to put that one equal to 1 because temperature doesn't enter the discussions here. And then there's going to be an energy here, which is defined in terms of r, and these unknown parameters theta. So the system which we have now is going to be defined in terms of the positions and these unknown parameters for the network, and we need to define this function e. So the simplest possible approach now is, if we think of this alternative 2 here, is that we replace the wave function with a Boltzmann distribution. Actually, this is going to be correct. The standard approach is actually to take the wave function squared. That's the standard approach. Some people have been playing around with letting the wave function be equal to the square of that quantity. But in the way we are going to implement it in the examples here is to say that the wave function squared, which represents a probability, is now being replaced by a Boltzmann distribution. Is there any questions so far about the technicalities which we are going to deal with? So let's now try to specialize and write down the type of Boltzmann machines which we can have. And let's remind ourselves also about some of the specific properties of a Boltzmann distribution. So what I'm going to do now is to simplify a little bit the formalism. So I'm going to rewrite this P of R of theta, and I'm going to rewrite that one in terms of a probability. And now I'm just looking at a one-dimensional problem. I'm just going to simplify life a little bit. So I'm going to have X, which is now going to be a vector, which contains the information about the input nodes. So we could write this in terms of a vector sign. And then it's going to be a function which depends on the hidden nodes. So these are vectors. So the first one represents the input values. And this one represents the hidden nodes. Now, the Boltzmann machines have a deficiency. And the deficiency lies in the fact that when you're setting up these Boltzmann distributions now, you are going to rely on a specific parameterization. So you can assume, for instance, that the X's and the H's take only binary values. So you could think of you sending an input 0, 1, and then that the hidden layer produces just an output, which is either 0 or 1. Alternatively, you can let the input values take a continuous set of variables, which is what we want. And then you can let the hidden nodes give just a 0, 1 in case they fire or not, in case they send a signal or not. You can also let the hidden nodes take a continuous, be given by continuous variables. So this is something which gives you flexibility in setting up the probability distribution. The problem, however, then, is that this set of probability distributions, they have their obvious limitations in the sense that they may not represent properly the physics which we are interested in. But however, they are extremely powerful methods which combined with some physics guidance. And that is why when we are dealing with the Boltzmann machine, it's useful to think of this. So this was the alternative 2. Sorry for forgetting that. If we do the alternative, if you look at the alternative 1, then we can use the Boltzmann machines as a way to get additional parameters to optimize and give us more flexibility in the optimization problem. But then we would multiply this Boltzmann distribution with a trial wave function, which we think gives already a good representation of the physics which we want to explore. So let's now look a little bit more in detail at this Boltzmann distribution. So in our case, we have just defined 2 sets of variables. Now, the partition function is just a normalization factor. So that would have an integral over dx and dh, if we are thinking of these as continuous variables. And then this partition function is then going to be given by the exponential here, where we have a temperature, T, and we are going to take that away. We're just going to put T equal to 1, and multiplied with this energy, or energy function, which depends on X and H. And these are the, obviously the coordinates of or represent the input layer and the output layer. Now, what you can do then, when you look at this, is because what we want at the end, we want a function, a trial function or probability for that, which depends only on X. And that means that what we will need is actually to integrate out the hidden nodes. So that means that we're going to get something which is called the marginal probability. So at the end, when we look at the probability distribution, we actually want to integrate out. So we are going to do something which goes like this, d of h, and then we are going to integrate out this Boltzmann distribution, and we will integrate away the hidden nodes. So at the end, we have something which is called a marginal probability. Let me just close the door here so we are not disturbed by the noise from outside. So this is normally called a marginal probability. For those of you who have taken a course in statistics and probability theory, you probably encountered this. So you are simply integrating out 1 degree of freedom, because at the end, we are just interested in the, when we have the optimal parameters, we are just interested in the spatial degrees of freedom in our specific case. Now, as I said, there are many ways by which we can now define this function E, the energy. So if we look at this one, and this is where we have the flexibility to define the type of modeling of the Boltzmann distribution. Now, by doing this, you will also see the limitations of a Boltzmann machine, because that will be limited by the way you model the specific functions. So the question is now, how do we actually model that? Now, one way to do it is now to have what's called a binary Boltzmann machine. Now, these Boltzmann machines, which you see here, which we are going to look at, if we go back to the figure which we have here, they are normally called restricted Boltzmann machines. They're called restricted because we are not allowing for connections between the nodes in a given layer. So you could actually have thought of having a connection between this node, connection with that one, a connection between this one, and so on internally in a given layer. That clearly will complicate the type of training which you're going to do. So a general Boltzmann machine has the possibility to have the connection between the nodes in the same layer. You can also stack these hidden layers. You can have more hidden layers, but what people have seen when they're training these Boltzmann machines is that that often leads to severe training problems, and in many cases you don't reach a proper convergence. So in many of the applications of these Boltzmann machines, people have ended up with what's called a restricted Boltzmann machine, where you now only connect the input nodes to the hidden nodes, and you have a full connectivity between the hidden nodes and the input nodes. So that means that this node here connects to all the hidden nodes, and similarly for all the other ones. So this one connects with everything else here, and so on. So if we now move down a little bit here, the simplest example which is used, and there's a reason why people use this, and the main reason is that what's called the marginal probability with these types of Boltzmann machines, they are given by analytical expressions, and that simplifies our calculations. So the first type of Boltzmann machine which many people will encounter is something which is called a binary Boltzmann machine. That means that the hidden layers and the output layers, they have nodes, the hidden layers and the input layers, they have nodes which produce either 0 or 1. And so this is a binary Boltzmann machine. And then we would define this function x of h in terms of, this is going to be a minus sign here. And then we have a sum over the input nodes, which we label as 1 up to n. There's going to be a bias for the input nodes as well. So there's going to be an input variable x of I. And this is multiplied with a of I, which is now plays the role of a bias. And there's going to be a similar object for the output, no, the hidden nodes. So this goes up to n, and this is going to have a bias b, and this is multiplied with the value of the hidden node, the output from the hidden node. So these quantities here, this x of I, take values which are just 0 and 1, and the same with the h of j. They take values which are 0 and 1. Now, for our case, this doesn't sound like a very useful thing because we need actually continuous variables for the x's. Now, there's an addition here. So let me just put this one in parentheses. And we have a minus, and then we have a double sum over I and j, which goes up to m and n. And then we have the weights, which these are the parameters which connect the hidden nodes with the input nodes. And this is multiplied with an x of I and an h of j. The quantity which is used more for this energy is something which is called a Gaussian binary. And for the harmonic oscillator type of the problem which we are dealing with, this is actually an optimal choice, because if you now think of the single particle wave function you had in project number 1, this was given by a Gaussian, where you had the argument x squared. So the Gaussian binary neural network, oh, by the way, I think, yeah, now let me just put this up properly here. X of h is given by a sum over I equal 1 up to n. And then we are having an x of I minus a parameter A of I, which is now representing the bias. So this A is a parameter which we need to train. You can have a variance here, but normally this variance is put to 1 in most applications. There is a minus, and then we have a similar parameter for the hidden nodes. So we have the hidden nodes have just a binary output. So the HJs, they take values between 0 and 1. And then we have finally we have the connection between the hidden layers and the input layer. So this runs the double sum, which runs over n and n. And then we would have an x of I, a wij, an h of j. And here as well, we could have a variance, a sigma ij. Now, normally the sigma ij, in most calculations, sigma ij is put to sigma I, and in most actual calculations, normally one puts this to 1. These are the two most common types of energy functions. And then when we have this representation here, we can actually then compute what is called the marginal probability. And when we have the marginal probability, we have something which can be used to calculate the wave function. I see that I'm going a little bit over time here. So let's now take a small break here and put the recording on. So to summarize what we discussed before the break, we want the first thing we're going to do now is to discuss the implementation of Boltzmann machines, which in a way is a slightly simpler way of implementing deep learning methods to a quantum mechanical study like the variational Monte Carlo study, which we did in project number 1. So this part of project number 2 deals with us replacing a correlated part of the trial wave function or the whole wave function with a neural network or a Boltzmann machine. So the what we will call the physics-guided way of doing that, which is named as alternative 1, is that we can take the best single particle wave function from project number 1, where in project number 1, we optimize these parameters alpha. And for the non-interacting case, we know that this alpha, depending on a choice of answers for the wave function, was given by alpha equal to 1, and we had only one parameter, because we could place all the different particles, or the bosons in this case, into just one single particle state. And for us, since we were chasing the ground state of the system, that means that we could place all the single particles which we have in the lowest lying single particle state. So the way one can proceed is to let either the Boltzmann machine or the neural network to figure out the correlated part of the wave function. Now, I should say that I've been involved with such calculations using neural networks, and neural networks give us something which is very close to what's called a diffusion Monte Carlo calculation. So a variational Monte Carlo calculation like the one which you did in project number 1 is normally used as an input to a diffusion Monte Carlo calculation. So a diffusion Monte Carlo calculation is a rewrite of Schrödinger's equation in complex time. And you can show that if you can simulate long enough, you should be able, with a given Hamiltonian, to reach the exact ground state of the system, or the lowest lying state with a given symmetry. So that's a very powerful technique. And diffusion Monte Carlo functions normally as a kind of benchmark for temperature equals 0 quantum mechanics problems. It functions as the benchmark calculation which all kind of approximative methods strive to reproduce. Now, so a variational Monte Carlo calculation doesn't give you more than the variational principle claims. So if you don't have the exact wave function, you will not get the exact energy. However, when you replace the correlated part of the trial wave function or the wave function itself with a neural network or Boltzmann machine, you can actually reach results which are extremely close to diffusion Monte Carlo calculations. And that's why these studies with deep learning methods have gained such a momentum in quantum mechanical studies. So the first paper, as I mentioned before the break, which is also cited in the references, is a paper by Carlo and Troyer, which appeared in Science in 2017. There's a reference in the lecture notes to the paper. And that paper really paved the way and opened up a huge set of activities concerned with using deep learning methods to solve quantum mechanical problems. So in principle, and we have seen that in calculations of systems like the electron gas, and also for dense infinite neutron matter, we get results which are basically the same as diffusion Monte Carlo results within statistical uncertainties. So we have an extreme flexibility here. The Boltzmann machines are kind of intermediate step. They had a lot of popularity in the beginning, but then people realized that the Boltzmann machines become a little bit more, they are less flexible than a neural network. So the two alternatives which we are going to explore in the project is to replace the full wave function with a neural network or a Boltzmann machine, or use alternative one, which is what we would call the physics-guided deep learning approach. Now, it's physics-guided also because one of the problems which many of these deep learning methods have had is to reproduce properly the symmetry of the wave function. So what we are doing now is to bake in to the calculation some specific symmetry requirements. So if you're dealing with fermions, what you would normally do then is that you would replace the correlated part of the wave function, the single particle part of the wave function, with a determinant, which is the way you would typically represent the anti-symmetry of the wave function. And then again, you would let the neural network or the Boltzmann machine explore the correlated part of the wave function. So to obtain the correct symmetry has been proven to be a tricky problem with the neural networks or deep learning methods in general. So the Boltzmann machine, I mentioned, it's very easy to implement, as we will see in the codes a little bit later today, but it has some, it is less flexible than a standard neural network. And the reason for the lack of flexibility is that you typically end up deciding upon a function for this energy, E here, this E of X of H. And that means that you need to, in the beginning of the calculation, you need to decide how you want to define that energy. And when you have defined that energy, then you can calculate what is called the marginal probability. So you're integrating away the hidden layers because you're not interested in them when you want to represent the final wave function. So the final wave function is going to be a quantity which is only given by the wave function as a function of X, or the positions. So one of these Boltzmann machines which was used, and in the original paper by Troyer and Carlo, they studied the quantum mechanical easing model. And the easing model is a model where you have outputs which are only given by a binary output. It could be -1 or +1 or 0 and 1. So for the description of the easing model, the quantum mechanical one, this is a pretty, how to say, intuitive way of setting up your function. However, when you deal with quantum mechanical problems like the one we are going to deal with, where the input would take continuous values, then what's normally been applied is a Gaussian binary. You can also implement a Gaussian so that the hidden nodes produce a continuous output. That means that you would replace this part here with a Gaussian, where you have an h of I minus a b, the bias squared, and divided with some kind of variance. Normally this variance, which you see here, is set to be equal to 1. Now, another quantity which one would normally set to 1, because we are not dealing with temperature here, is actually the 1 over t here is normally set to 1. So that means that the quantity which you're going to look at is the exponential of, with an argument minus the energy which you opt for. Okay. So I also wanted to bring up the slides where we have the material for everything we're going to discuss now. So what I'm going to do now is to guide you a little bit through the derivation of these different probabilities. And then when we have these equations, we can then implement them in a code which is going to look pretty close to the Python codes which I showed you when we worked on project number 1. So let's take a look at where we have the material. So I'm going to jump out of the whiteboard and go back to this basic material which we have. And what I've done here, if you now look at this, so this is the basic GitHub entry point. If you then go into the Jupyter book which we have and click on that one, so this is the link up here, that gives you a kind of collection of material which we have been teaching throughout the years in this course. So we've also been doing standard many-body physics. And if you scroll down here, you will see that there is a chapter 14 which contains the description of these Boltzmann machines and a kind of basic theory which we are going to discuss. Now, there's also some basic material about neural networks which we are going to come back to after the coming holidays. So that will be on Thursday, April 21. If I've done the counting correctly, because we are April 7 now, right? So in the beginning here, you would find some of the basic motivation for Boltzmann machines, and the typical Boltzmann machines which are used are binary. So RBM stands for restricted Boltzmann machines. And the reason why they're called restricted, as we discussed before the break, is that these Boltzmann machines, they do not have a connection between the nodes in a given layer. So a full Boltzmann machine has a full connectivity. And that has been shown in practical applications to be pretty hard to train. So what we are going to deal with essentially for this project is a Gaussian binary Boltzmann machine. The reason why we do that is just simply because it's easier to implement. It gives a better description of the trial wave function, which we are interested in, because the single particle piece depends on that. We will miss parts which describe properly the correlations. And you will see that the Boltzmann machine is not going to give you a result which is much better than what you had in project number 1. But if you implement a neural network, you're going to get better results. Although in our case, the trial wave function is a function where the interaction piece is weak, which means that the single particle piece gives us already a very, very good reproduction of the data. So when you're dealing with the Boltzmann machines, and this is something we can come back to, you can also use other types of units here. So you can have a softmax and multinomial units, Gaussian visible and hidden units, and many other types of ways to represent this function E. So let's go down a little bit in the slides here. And I'm just going to skip this function which you have here. If we now do a quantum Boltzmann machine, this is very much based on this article by Carlo and Troyer. So they applied this to quantum mechanical spin lattice systems of the Ising model and Heisenberg type. And I know that some of you are actually dealing with that. And in that specific case, they actually implemented a binary restricted Boltzmann machines. where the nodes could take only a binary output, which is either 1 or -1. Now, what we are going to do now is to let the wave function, so I define this as an F here, to be represented by this Boltzmann machine. And as I said, you normally put this temperature T equal to 1. So which means that what you end up with is a function of this type here. Now, in the paper by Carlo and Troyer, they experimented with a wave function which was given by just the Boltzmann machine, or they took and squared it in order for that to represent a quantum mechanical distribution. So this is something which one can also explore. What we found is that if we take the wave function squared here in equation 29, what we discovered then is, what we saw in practical calculations, is that that normally gave a slightly better result. And that will also be closer to the physical interpretation of what you have. So these are normally called a neural network quantum state. And if you now look at your wave function, what you need then is to compute what's called the marginal probability. So it means that we need to sum over the hidden nodes, which we have, as you can see here. And if you do that, you need to perform the summation here where you plug in the energy. So there are some boring details, and I'm going to take the liberty of actually going through them through the slides here, because it's not so exciting to calculate these quantities. So when you now sum over h here, because you want to have a function which is just given by the sum of these h's, you want it to depend only on x, then you get a probability distribution, which is the marginal distribution, which now takes this analytical form here. So one reason why you end up using these kind of energy functions, binary, or Gaussian binary, or Gaussian, is that these manipulations which you see, this sum over h, can be done analytically. Now, then you need to choose the cost function. So in a neural network or in any machine learning method, you need to find a way by which you can optimize your model, and your model is given by either a neural network or any other of the machine learning algorithms. So the neural network or the Boltzmann machine is our model. And in this case, what we are doing now is simply to calculate the derivative of the energy with respect to the parameters theta. And remember now that we defined this parameters theta to be equal to the weights and the biases of the network. So are the quantities which we also defined in project number 1. So you already have a code for these quantities here. This means that you can reuse that one. The thing you would need to do is to replace your wave function with equation 32. And in the training, when you're optimizing your cost function, so the cost function or risk function or error function as it's being called, is now simply being given by the derivative of the energy here. And you want to optimize that one, and you want to have that one equal to 0. And everything is also driven by the local energy, which is given by 1 over psi, and then the Hamiltonian multiplied with psi. Now, the reason why I would like to propose in this project number 2, for those of you who want to venture into neural networks, why I would like to propose starting with a Boltzmann machine is that we can easily then reuse everything we have done in project 1. And the only thing we need to do then is simply to implement a new trial wave function and then calculate the same quantities as we did before. So in the optimization now, what we are going to optimize is this function here, and we want to drive that one to 0, period. Because we want to be at the minimum of the expectation value of the energy. Let's take a small, let's stop a little bit now and see if you're with me in the basic philosophy of what we are going to do here. Are there any questions things which are unclear? Is the overarching aim clear to you? Do you see what you have to do in order to implement this first approach to deep learning? So feel free to unmute yourself if you have questions, or just use the chat. Still no question, guys. I have to pay some of you to ask questions. So the overarching view now is that we are going to optimize this function with a given trial function, which is going to depend on the parameters A, which you see here, the parameters B, and the parameters W. So this is the quantity which we are going to implement in the code. So when we've chosen the cost function, what comes here are actually some mathematical details. And feel free to look at them. There is no need for you to derive all these mathematical details. You can just use the equations and then simply implement them in the code. So if you look at these quantities, clearly the quantity like the partition function, since we are going to use the Metropolis algorithm, we are only going to look at ratios between probabilities. And that means that the partition function itself is something which we don't need to deal with. So we can now rewrite this function in a more general way in terms of this function E, which is normally called an energy function. And then we will typically have a product over different variables C here. And the standard Boltzmann machine, which we have, is given by these parameters, which you see here. The typical function, as we described, this will be a much more general expression. But we are going to simply have a function which is now reduced to the simpler one, which runs like the one which you see here. And then what follows here is just a series of manipulations in order to show you how you reach the correct distribution which we need to implement. So you can also define different probabilities. You need also the probabilities, the reduced probability for the hidden nodes. You can also use Bayes' theorem. There are lots of small manipulations here, and I'm not going to go through this in all detail. But if you look at the simpler case, like the binary case, which is this one, then you have a pretty, since a BB stands for a binary Boltzmann machine, you have a pretty simple expression for the final probability. And then the thing which is interesting for us is actually to calculate the marginal probability functions. And this is the quantity which we want. In our case, these h's are not given by an integral, but by a summation, because they take binary values. And in our case, we can actually calculate this. And what you will find here is actually the derivation which leads to the expression which we are going to code. So this is not very exciting, but I plugged it in here as a kind of background, and you can look up these details in order to convince yourself about the correct expressions. So that leads to general marginal probabilities for both the hidden nodes and the visible nodes, as they're normally called, or the input nodes. So for Boltzmann machine, one normally calls the input layer for the visible layer, because that's the one where you keep manipulating the values of the x's. And the other thing which you also may need is a conditional probability. But the quantity which we will end up dealing with is actually the Gaussian binary restricted Boltzmann machines. And you can then calculate the joint probability distribution with a partition function, which we actually don't need. So these equations are just put up for the sake of completeness. And please apologize me for not going through all these equations when we are discussing their derivations, because this is just you or us performing either integrals or these summations. And the quantities which are interesting for us when we are going to simulate things are these probability distributions. And these are the things which we need to implement when we now are going to optimize the Boltzmann distribution. So the Boltzmann distribution here plays the role of our trial wave function. So I'm just going through here so you can see the different equations and how they appear. And at the end, after all these boring exercises, we end up with a function of this type here, which we now want to optimize. And this equation, which you see here, this 78, is the equation which we are going to implement in our code. So the standard way of doing this now is to rather think of this as a probability distribution. So when Troyer and Carlo did the original study, they played around with the wave function being given by the Boltzmann distribution, or the wave function squared, which is a standard quantum mechanical distribution given by the Boltzmann distribution. Now, if you look at this expression here doesn't know much about the symmetry of the wave function. So what many people actually do when they use these Boltzmann distributions is to see as a Boltzmann distribution as something which gives you an additional flexibility in fitting the energy. So you would then multiply this one with some physics guidance, which could be, in the case of fermions, it could be given by a determinant, which then accounts for the anti-symmetry. Alternatively, you can multiply this one for the case of bosons with a symmetric function, which is the product of single particle wave functions. And this is what essentially what we did in project number 1. So you could now think of this guy here, this FRBM, to be the function which gives you the flexibility to find correlations. And then you would multiply it with the single particle wave function, which you optimize from project number 1. And in this case, when you now think of this as a quantum mechanical distribution, then your wave function will be the square root of this quantity here. And if you do the algebra here, you simply get a square root factor. And that is when you take the log now in the actual calculations, it just gives you a factor of a half. So we are going to take the log of this function here. And if you now look at the wave function, if you look at the cost function which we want to optimize, this is exactly the same as we had in project number 1. These alphas are the variational parameters, which in our case become the biases of the visible layer or the input layer, of the hidden layer, and the weights. So we will need to take the derivatives with respect to all these parameters. Now, what is convenient to do now is to take the log of the wave function, because if you look at this function which you have here, this is actually the derivative of the log, nothing but that. So it's, if you take the derivative of the log of this function, the logarithm, then this square root gives you just an additional factor of a half. And there is actually no specific complication in doing that. So what I have here are the analytical derivatives of this specific function with respect to the biases of the visible layer, the biases of the hidden layer, and the weights themselves. And these are quantities which we will need to implement when we are looking at derivatives. So you see now that you have explicit analytical expressions for these derivatives. Now, when you're dealing with these Boltzmann machines, you're a little bit limited in the sense that you want to have analytical expressions for the derivatives. You can alternatively calculate the derivatives using automatic differentiation, but that leads to more CPU cycles. So using a binary expression or a Gaussian binary expression is something which gives us analytical expressions for the derivatives. Now, I hope you can forgive me also for not going through all these derivatives on the whiteboard, because this is not a what I might call an exciting thing to do. we know how to take derivatives. So I hope you there can forgive me for just stating the expressions, because these are the expressions which at the end we need to code. So this is the case when we take the wave function as the probability. If we take the wave function squared, that means that we need to take the square root of the Boltzmann distribution. Then we simply get just this factor over half in front of things. And you see now that mathematically, when we recognize what you have here as the derivative of the logarithm of the wave function or the probability, then the only difference between one interpretation and the other one is that we have a factor over half in the derivatives here. Then our Hamiltonian, in this specific case, the example which I have used, I have the harmonic oscillator, which we have done before. And then we have a Coulomb interaction. Now we are going to replace that one with the interaction which we have from project number 1. But the example which follows here is actually something which now uses this specific term here. So it means that when we calculate this term, what we have then is the standard expression for the Hamiltonian, which we discussed also in project number 1. So we have the operator here acting on a trial wave function. And now we have to be a little bit more careful, because now the trial wave function is a quantity which is defined by the Boltzmann machine, or the Boltzmann machine multiplied with something else. So the local energy then, which we get, is now, this is the quantity we need to integrate. So we would then have the local energy, which is given in terms of these derivatives, plus the interaction piece. So when we are dealing with the harmonic oscillator, what we have is a pretty compact expression here. So if you now start doing this, implementing a Boltzmann machine without the interaction, and this is what I would advise you to do in the beginning, the quantities which we need to deal with are actually given by the first part here. So if you can see my arrow, the quantities we will need to implement, actually these three first terms here, without the final one in equation 106. So this means that depending on how we are going to do this, we can now have a function which we calculate numerically, derivatives, or we can plug in an analytical expression. So if we plug in just the plain Boltzmann machine, we actually have analytical expression for these quantities. And this is something which is worth considering. But at the end, we are going to have more complicated trial functions. And then it's more convenient to use automatic differentiation packages. And one is JAX or AutoDiff, which for those of you who've been programming in Python, you're pretty familiar with. In C++, you have a package called automatic differentiation, or just AutoDiff, which you can implement. You also have, I know that some of you are planning to write in Julia, and in Julia you also have automatic differentiation. So the equations which we need to set up in order to run a Boltzmann machine are essentially this equation for the local energy, which now depends. So this is just a slightly more compact way than what we did in project number 1. And we need to have the derivatives of the log of the trial wave function. And these derivatives are, in our case, when we plug in a Boltzmann machine, they are simply given by this analytical expression here, which then depends on the weights and the biases. And then what we need then, when we have everything in place, this is what we simply need now, is to decide whether we want to use a quantum mechanical distribution where we have the wave function squared, which means that we need the square root, and that just introduces this factor over half. Or we want to run it with the wave function being represented by the Boltzmann machine. Now, the Python version for the two non-interacting particles is something which is given at the end of this chapter. And I just wanted to step you through the basic elements because they can serve as a guidance for what you want to do now in project number 2. So I would, in the first step is to implement this simple Boltzmann machine, but implement it in either 1, 2, or 3 dimensions as you did in project 1. And then just look at either 1 particle or 2 particles or many. And then just check that you actually get the correct energy for the non-interacting case. And we know the value for that. So let me try to step you through the basics of the program. So, and let me remind you of what we need. So what we are going to optimize and drive to 0 is equation 90. And equation 90 depends on the new parameters. So these are no longer your variational parameters, but these are now the biases of the visible layer or input layer, the biases of the hidden layer, and the weights, which connect the visible layer with the hidden layer. And we need to optimize this equation 90 here, and we want to drive this to 0, because that's where we expect to have a minimum. Now, the energy, as we also discussed before, is a convex function, which means that we're also going to get a global, hopefully, we are going to get a global minimum for the energy. The technical details we need to think of then is first, deep psi with respect to the derivative here with respect to one of the parameters and multiplied with the inverse wave function. This is nothing but the derivative of the logarithm, as you can see here. So if you look at this equation, this term here, we know that this is just simply the derivative of the logarithm of the function. This is very helpful when we are now setting up a Boltzmann machine, because the Boltzmann machines are given in terms of exponentials. So when we take the log of the Boltzmann distribution, we simply reduce that one to sums here. And that really simplifies life for us. And the only thing we need to do then is just to be a little bit careful when we are calculating derivatives. And in our case, then what we have are now derivatives which are a little bit more complicated, but not that complicated. And if we have a quantum mechanical distribution, then we need to take the square root of the Boltzmann distribution in order to get the quantum mechanical wave function. We are assuming that our functions are real here, and the harmonic oscillator is actually a wave function which is real. And the quantities we end up with then are these derivatives which we need to evaluate. And we need then also to set in the Hamiltonian. And in our case, the first step is actually to just take the non-interacting case. And there we know what we need to calculate. So we would need to calculate this in order to set up the local energy. For the harmonic oscillator, these quantities are quantities which we can calculate, as you can see here. So we have analytical expressions for them. And then we can simply go back and implement these as we did in project number 1. So let me try to show you now how we're going to do this. So what I've done is to implement the Gaussian binary Boltzmann machine. And then that means that my wave function now takes the positions R, the biases of the visible layer or input layer, the bias of the hidden layer B, and the weights. I put this sigma to 1, and then I have a factor here which I'm setting up, this factor Q, which I'm coming back to. And then I run over the number of particles, and then I run over the number of hidden nodes. So I'm setting up the contributions to the wave function. So what you see here is me just implementing this new trial wave function, which contains one contribution from the visible layer and one contribution from the hidden layer. And then I'm setting up the local energy, which again depends on the positions and the parameters of the neural network or the Boltzmann machine. And then I'm simply summing up over the number of particles, and I'm calculating the energies. And you see here I have the derivatives. So I'm using these analytical expressions which I had. These expressions here can be obviously be replaced by expressions from either numerical derivation or from the usage of automatic differentiation, if you prefer that. And normally I recommend using automatic differentiation. So this is the ln of the psi1, which is, so psi1, if we go back, that would be the part which deals with the visible part. So that would be the derivative of this quantity here, this specific part here. And then we have a similar derivative, which is a derivative with respect to the weights, which we also need to set up. And then we can put up the final expression for the local energy as we have them in these analytical expressions. And if the interaction is true, we can also do that. And then we can, in this specific case, I have a Coulomb interaction. And that depends only on the relative distance of the two particles. And then I have the derivatives, so which is needed when I'm now also setting up the optimization of the so-called cost function, which is actually the derivative of my wave function ansatz, with respect to the variational parameters, which in our case are given by the weights and biases of the neural network. Then you have the quantum force. And in all these calculations, what you will see is that I am implementing this wave function given by a Boltzmann machine. So this is what I call alternative 2 in the beginning of the previous lecture. So there is no physics guidance here. Then this factor Q here is just the factor which relates to the hidden layers. And if you go back to the equations, you will see that this is now a factor which runs over the biases of the hidden layers. And then I have my energy minimization, which is actually my standard Monte Carlo piece. I run over the number of Monte Carlo cycles. I set up the old position. I do the new position. I calculate the quantum force. I'm actually dealing with importance sampling. So this is exactly as before. So the difference now resides in me implementing another type of wave function. That's the basic difference between what you did in project 1 and you're going to do in project 2. In this particular case, I've chosen a Gaussian binary Boltzmann machine, and I have analytical expressions for all the derivatives. Now, what you would need to do is, if you want to use this, I would actually recommend to start with your program from project 1 and replace your trial wave function with a Boltzmann machine. So that's the first step, and look at the non-interacting case. So what comes here after this one is just a standard Monte Carlo looping. We run over the number of Monte Carlo cycles. We set up the Metropolis test, which comes in here. So that's the Metropolis Hastings, is exactly as before. And you will see that this function is nothing but the one which we discussed in project number 1. And then what I'm calculating are the derivatives of the log of the wave function. I have my local energy, and I calculate these integrals because these are the integrals which I need in evaluating the cost function. So if you go back to the slides, no, to the material we have here, I need to calculate this same quantity which we had in project 1, the same integrals, except that now I'm just replacing this trial wave function with a Boltzmann machine. And that gives me different expressions for the trial wave function. With that, we can continue as we did before. And you see now that I also have my standard procedure. I calculate these different derivatives. In this case, what I'm doing now is to set up the number of particles to be equal to the number of hidden layers. And I have 2 dimensions. This means that my input layer has 4 nodes. I have 2 particles times 2 dimensions. And then I say that the number of hidden layers is just given by 2 in order to reflect the number of particles which I have. And that means that when I'm setting up my initial guess for the parameters, you can now see that I'm setting up the biases to be given by a normal distribution, where I actually put them to a small dimensionality. So this one is given by the number of particles in dimensions. The B value is just given by the number of hidden nodes. And the weights are now given by number of particles, the dimensions, and the number of hidden here. So that's the size of my weights. Then I'm simply calculating the derivatives. I'm initializing these quantities. And in this particular case, I'm still doing this very, very brute force way of optimizing my trial, my cost function, the derivative of the energy. So I'm just setting up a so-called second derivative, which is given by this parameter eta, and it's normally called a learning rate in machine learning language when you're dealing with neural networks or any other procedure where we are replacing the second derivative or the Hessian matrix with a parameter. I set up the number of max iterations to 50. This is a pretty stupid way of doing it, and my previous code was also not very refined. And I simply calculated different gradients for the biases, for the visible layer, the hidden layer, and then the bias, or no, the weights for the gradient for the weights here. So I have 3 sets of derivatives. I calculate the gradients, and then I keep iterating till my gradient should vanish. And then you can now see that after these 50 iterations here, so the exact energy, remember that the exact energy should actually be equal to 2. So my first guess is pretty close, and that's also because I started with a Gaussian binary distribution. And this is just going to jump back and forth, but you see now that after these 50 iterations, you would typically see now that the final energy is close to 2 here, which it should be. So using this Boltzmann machine and running this code here, I'm getting a result for the non-interacting case, which is pretty close to what we should get. I see I'm running a little bit over time, but take a look at this section 14.6, because that essentially gives you all the mathematical details which are needed for setting up a Boltzmann machine where your trial wave function is given by the Boltzmann machine only. So there is no physics guidance here. And we happen to be lucky because we chose a Gaussian probability for the visible layer. And we know that the trial wave function should have something which reminds us of a Gaussian because we have the harmonic oscillator. And then take a look at the Python code here and go back to your project 1 and replace the trial wave function with the Boltzmann machine and try to run your code for 1, 2, perhaps even 10 particles and see how well this does in reproducing the exact energy which you have for the non-interacting case. I'm going to refine the project text so that we can bake in these different baby steps. But I wanted to present the basic overarching idea to you today. And then when we are done with the Boltzmann machines, and depending on how much time we have, we could then dive into neural networks. So that means that after the break, after the holidays, I'm going to discuss how you can implement a neural network and replace your trial wave function with a neural network. So I'm going to stop here.